Welcome to our Quantum Deep Dive. Today, we are diving into the incredible work of a true architect of the second quantum revolution, Peter Zoller. And we're doing it based on a really fantastic, in-depth essay by Jörg O. Schneppot.
You know, the essay describes Zoller with this one key phrase that I think just nails it, and it's going to be our theme today. He's a bridge builder. He's someone who just masterfully connects that really abstract, high-level theory with stuff you can actually build and test in a lab.
So, to really get a handle on his impact, here's the path we're going to take. We'll start with his origins, see how his vision was forged abroad, then get into the nitty-gritty of his ion trap blueprint. From there, we'll look at how he dreamed up quantum simulators and even a quantum internet. And finally, we'll talk about the legacy he's built. Okay, let's dive in.
All right, so let's rewind the clock. Our story kicks off in Innsbruck, Austria. Peter Zoller was born there back in 1952. And even when he was young, he had this amazing knack for looking at the world around him and seeing the universal laws of physics at play.
So naturally, this passion took him to the University of Innsbruck. But here's the thing. He wasn't just hitting the books. He started to see how theory could be this powerful tool to actively shape and guide real experiments. He was just captivated by this idea that you could take these incredibly complex natural processes and boil them down to a few core principles. And that way of thinking, it became the absolute hallmark of his entire career.
Okay, so after getting his doctorate in '77, Zoller knew he couldn't just stay put. If he wanted to make a real splash, he had to get out there and immerse himself in the global physics scene. And that journey took him to the United States.
So you can see the path here. He goes from Innsbruck to the University of Southern California, and then, and this is a big one, to the Gila Institute in Colorado. This time away was just absolutely critical. This is where he starts working shoulder to shoulder with the world's best minds in quantum optics, really diving deep into the most cutting-edge research happening at the time.
Right, and that experience at Gila, it was totally transformative. It wasn't just some research gig. It was this melting pot where theory and experiment were just two sides of the same coin. The source really points out how this place forged Zoller's identity as a mediator. This is where he perfected his role as a translator. You know, someone who could take these wild-looking equations and turn them into a concrete to-do list for folks in the lab.
So, armed with this whole new way of thinking, Zoller heads back to Innsbruck. And this is where he starts the work that would truly define his legacy. He teams up with an experimentalist named Rainer Blatt. And their collaboration, well, it's now basically a textbook example of how to do physics right.
I mean, talk about a big question. This is what they set out to answer. And the solution they came up with, published in 1995 with Ignacio Cirac, was this incredibly clear and practical blueprint. Their paper became, and this is no exaggeration, a foundational text for an entire field.
And this just shows you the pure elegance of their model. It's a simple four-step recipe. First, you trap the ions. Then, you store information inside them. You get them to talk to each other using their shared vibrations. And finally, you control the whole shebang with lasers. The reason this was so revolutionary was that it wasn't just a beautiful theory on paper. It was a practical, step-by-step guide that experimentalists could actually go out and build. It was that bridge we were talking about, connecting the world of math to the world of the lab. Okay, so let's pause on the most crucial ingredient here, the qubit. This thing is the absolute heart of quantum computing. You know, classical computers have bits. They're either a 0 or a 1, on or off. But for quantum, we needed a whole new building block.
The best way to think about it is this. If a classical bit is like a light switch, it's either on or off, 1 or 0, a qubit is like a dimmer switch. It can be on, it can be off, or it can be in some combination of both states at the exact same time. And that ability, that superposition, is what unlocks this mind-boggling amount of computational power. And Zoller and Cirac didn't just have the idea, they wrote down the exact mathematical recipe for it. Now, you're looking at what's called a Hamiltonian. Don't worry about the symbols. What's so important here is that this equation is a precise set of instructions. It literally tells the people in the lab exactly how to tune their lasers to make two of those ions talk to each other and perform a calculation. It's the playbook for their quantum choreography.
But Zoller wasn't done, not by a long shot. Building a quantum computer wasn't the only mountain to climb. He also laid out the theoretical plans for two other game-changing technologies, quantum simulators and the quantum internet.
So first, simulation. He came up with this idea of using lasers to create something called an optical lattice. Think of it as a virtual crystal made entirely of light. You can then trap supercold atoms in it. This gives scientists a tool they've only dreamed of. They can now simulate really exotic materials like high-temperature superconductors in a perfectly controlled lab setting. This is stuff that even the most powerful supercomputers today can't handle, and it could open the door to discovering all kinds of new materials.
Okay, next up, communication. This one is a huge hurdle. Quantum states are unbelievably fragile. I mean, the slightest little interaction with the outside world can just obliterate the information they're holding. So that presents a massive challenge if you want to build, say, a secure quantum network that spans a whole city or even a country.
And here's the brilliant solution Zoller and his colleagues designed, the quantum repeater. Instead of trying to send one fragile particle the entire distance, you create a chain of shorter entangled links. Then, at each connecting point, you do this clever trick called entanglement swapping. It's kind of like passing a secret handshake down a long line of people. Each pair in the line shares the handshake, and then, by doing a special operation in the middle, you can transfer that handshake from the very first person all the way to the last, creating one long, unbreakable connection. This is the technique that paves the way for a future quantum internet.
So, when you step back and look at it all, you can see how the blueprints Zoller created sent these massive shockwaves through the entire field of quantum science. He established fundamental concepts and inspired a whole new generation of researchers.
And, it wasn't just about the theories themselves. He literally helped write the dictionary for quantum technology. Terms that we now take for granted like quantum gate or quantum repeater, they became standard in the field in large part because of his foundational work. That kind of clarity was just essential for turning these abstract thoughts into real engineering goals.
And, as you totally expect, the recognition started pouring in. His contributions have been celebrated with some of the highest honors in physics, including the super prestigious Wolf Prize back in 2005. The Wolf Foundation even specifically called out his groundbreaking work on quantum information and that ion trap computer.
But what's really amazing is that beyond his own research, he played this huge strategic role. He helped get massive international projects off the ground, like the EU's quantum flagship. So he wasn't just in the lab, he was in the boardroom, helping guide billions in funding to speed up the very quantum revolution that he helped kickstart.
And this quote, wow, it just sums up his whole philosophy perfectly, doesn't it? His entire career has been this powerful testament to the synergy you get when you combine deep, theoretical thinking with real-world, tangible applications. He really is the ideal physicist.
So Peter Zoller gave us the architectural plans for a whole new technological world. The question he leaves for the next generation of scientists and engineers, and really for all of us, is what are we going to build with it? And that brings us to the end of our deep dive on the incredible work of Peter Zoller. This whole explainer was made possible by the really insightful essay from Jörg O. Schneppot. To read the full piece and check out his other work, please visit schneppot.de. Thanks so much for joining us, and goodbye.
Schneppot.de is a private project by Jörg O. Schneppot dedicated to promoting quantum technology. Its mission is to present knowledge in a way that is clear, precise, and transparent for those just starting out, as well as for experts who wish to deepen their expertise. He firmly believes that education and access to well-structured information are the keys to unlocking the full potential of this future technology. If his work helps you realize your own visions and actively and consciously shape quantum technology, then the goal of his project has been achieved.